So, good evening. I'm going to share my slides. Is the slides visible? I hope it is so. So, good evening. Welcome to week 5 tutorials of NPTEL PMRF tutorials of the course Pericyclic Reactions and Organic Photochemistry by Professor S. Shangaraman from IIT Madras. Myself, Anisha Suresh, PMRF TA for this course from IIT Bombay. So, in week 5, mostly chelotropic reactions have been discussed along with some extension to sigmatropic rearrangements. So, this week we will be discussing some more problems regarding sigmatropic rearrangement, and we will be discussing few problems regarding chelotropic rearrangement as well. So, coming to the first question, predict the cope rearrangement product of the reaction. So, this is the starting material. It is subjected for heating and we are asked to find out the rearrangement product. So as we can see, this is like a 3, 2, 1, 3, 2, 1. It is a system which can undergo 3 3 sigmatropic rearrangement. So 3 3 sigmatropic rearrangement is also known as cope rearrangement. So we are having the system. So this will be this is the we are numbering the total number of atoms. So if we are giving the numbering according to the 3 3 sigmatropic rearrangement, it will be 3 2 1 and 3 2 1. So this bond will this double bond will attack here, this will shift here, and this bond will break and it will shift here, leading to the opening of the strained cyclopropane ring, leading to formation of a 7-membered ring. So this is the product that we are getting in this reaction. So is the mechanism of this reaction clear? So first of all, we have to number the system in order to know if it is a 3 3 sigmatropic rearrangement that is taking place. So you can number like this. So the double bonds will be getting 3. So 3, 2, 1, 3, 2, 1. Then the bond displacement will take place. And since this is a strain cyclopropane ring, so the releasing of this strain can be a reason for the proceeding of this reaction. Okay. Now, coming to the second question. So this is the second question. So here we are asked to find the or the predict the product of the following reaction. So here we are having a dialkene or diene system. So if we are numbering it like 3, 2, 1, 3, 2, 1. So we can see that the system can undergo a 3 3 sigmatropic rearrangement. The system can undergo a 3 3 sigmatropic rearrangement. So we can and since it is involving an oxygen, this can be called as a Claisen rearrangement. So the mechanism can be written like this: 3 2 1 3 2 1. This bond will come attack here, this bond will shift here, this bond will break, and a double bond will be forming here. So a system like this will be resulting. So this is an enol kind of system. So it will undergo tautomerization to give the more stable ketone. So this will be the final product of the reaction. So here two reactions are taking place. First a 3,3 sigmatropic rearrangement. So since it is involving oxygen, this can be called as a Claisen rearrangement. Once the C3 sigmatropic rearrangement have taken place, we will get a molecule like this, which is having an enol. So we know that compared to enol, ketone will be more stable. So it will undergo a tautomerization, resulting in the formation of the ketone. So is the mechanism clear? I hope it is clear. Now we will be moving towards the question number 3. So here we are asked to predict the product of the following Claisen rearrangement. So this will also undergo a 3,3 sigmatropic rearrangement. So we can number like this. So this will be 3, 2, 1, and this will be 3, 2, 1. So we have to rotate this bond so that these two double bonds will come in proximity. Okay. So we have carried out bond rotation so that these two double bonds will be coming in proximity. Then this double bond will go and attack over here. This double bond will shift here. This bond will break and lead to formation of a carbonyl. So once the rearrangement is done, we will get a system like this. So this oxygen which was attached to carbon number 3 have now become a substituent of carbon number 1, and it involves now a carbonyl instead of an ether. Okay. So a bond migration have taken place here. So here also 3,3 sigmatropic rearrangement is what that is taking place. So we can number it like 3, 2, 1, 3, 2, 1. Then we do a bond rotation so that these two double bonds will be coming in proximity, and then we have carried out the 3,3 sigmatropic rearrangement. So we will get this as the major product. Clear? Moving to the fourth question. So here, predict the product of the following Claisen rearrangement. So hint, think carefully about the most stable structure for your product. So we are getting some unstable product maybe after carrying out the Claisen rearrangement. So we have to hmm, modify it so as to get the stable structure. So here also we are planning for a Claisen rearrangement. So it is a 3,3 sigmatropic rearrangement. So this can be written like 3, 2, 1, 3, 2, 1. So here the aromatic double bond is taking place in the rearrangement. So we can see like 3, 2, 1, 3, 2, 1. So this double bond will go and attack over here. This double bond will break, shift over here. This bond will break and it will lead to formation of a carbonyl. So this is the system that we will get. But what is the problem? Here the aromaticity of this benzene ring is gone. So in order to regain the aromaticity, this ketone will undergo tautomerism and it will result in the formation of this enol. So we will get this phenol as the final product. So in previous case we have seen that enol is less stable compared to the ketone. But here, since this is an aromatic system, this was an aromatic system, and after the 3,3 sigmatropic rearrangement, the aromaticity of the product is lost. So it will try to regain the aromaticity. So because of that, here the ketone is less stable compared to that of the enol. Okay. So here also this reaction is taking place in two steps. First, it will undergo a 3,3 sigmatropic rearrangement, and then this unstable ketone, because of the loss of aromaticity, it will undergo a tautomerization reaction. So this ketone will convert it to an enol, and it will result in this final stable product. Okay. Now coming to the question number 5. So here we are given a ketyl, and this is an allyl alcohol in presence of acetic acid. It is giving this product. So we are asked to propose a mechanism for this Claisen reaction. So here they have asked, your mechanism must generate an allyl vinyl ether so the Claisen rearrangement can occur. So this is a hint. The mechanism should go through an allyl vinyl ether. So keeping in mind our starting materials and the reagent, that is acetic acid, we have to propose the mechanism. Now coming towards the mechanism, in the presence of acetic acid, this ketal, here the OMe will abstract the proton from acetic acid and it will get protonated. Now, this lone pair on this oxygen atom, when it is falling down, this protonated OMe, it will get removed as methanol. Now we are having a positive charge on the oxygen, that is, this center will be more activated. So this center will be more electrophilic, and this is the other starting material we are having, that is the allylic alcohol. Now the lone pair on the oxygen will attack on the carbonyl carbon, and this positive charge will be neutralized. So we get this product. And now we are having a hydrogen atom on this allylic alcohol that will be abstracted by this oxygen lone pairs, and we will get this intermediate. And once the lone pair on this oxygen will be falling down, elimination of methanol will be taking place. So we get this intermediate. Now a counteranion of acetic acid will be present in the medium. It will abstract the proton. This will be acidic proton. This acidic proton will be abstracted. So here this a double bond formation will take place, and the positive charge on this oxygen will be neutralized. So we have got an allyl vinyl ether. So this is the intermediate that was discussed in the question. Now this can undergo a 3,3 sigmatropic rearrangement. As we can see, 3, 2, 1, 3, 2, 1. So it will undergo a 3,3 sigmatropic rearrangement, which is also known as Claisen rearrangement. So this double bond will shift here, this will shift here, and this bond will break. So what we will get is this product. So they have rearranged and wrote. So what we will be getting is like R double bond O. Here a new bond is formed. So this is the product that we will get, and this is similar to this. So you can follow the numbering so that you will not get confused. So this is the mechanism for the reaction. So this is a general mechanism. This is following a Claisen rearrangement. If we are having an OME here, it is known as Johnson-Claisen rearrangement. And now we will be seeing another question where it is Eschen-Mosher-Claisen rearrangement. Okay. So is the mechanism of this rearrangement clear? This question I think is little bit easy. Mechanism is easy to understand. Now coming to the question number 6. So it is following a similar mechanism, but here an amine is involved. So because of that, this reaction is known as Eschen-Mosher-Claisen rearrangement. So what will be the product that we will be getting? So following the mechanism that we have seen previously, this will be the product that is resulting. We will attempt the mechanism again. So we are having a ketal like this in the presence of acetic acid. This lone pair will abstract this proton and OAC will leave, and we will be getting OMe, OMe, H plus NMe2. Then this lone pair will fall down. This will get removed. So minus methanol, here minus OAC minus. So we will be getting NMe2 double bond OMe plus. So this is an electrophilic system. Now what will happen? This allylic alcohol will attack here, neutralize this positive charge, and we will be getting OMe, OH, NMe2. So here a positive charge will be there. Now this proton will be abstracted and we will be getting NMe2 OMe H plus O ally. Now this lone pair will fall here. Methanol will be eliminated. NMe2 double bond O plus now this is the acidic proton. OAC minus will be present in the medium. It will abstract this proton and we will get the allyl vinyl ether. So double bond O NMe2. Now we can, this is the intermediate that will undergo the Claisen reaction. So we can number it like 3, 2, 1, 3, 2, 1. So this will attack over here. This bond will, double bond will form. This bond will break. And we will get this product. Means NMe2 double bond O. So here CH2, one more CH2, One CH2, one more CH2, one, two, three, four. One, two, three, four. And here double bond will be there. Okay, this is the final product that we will be getting. The mechanism is clear. So this is known as Eschen-Mosher-Claisen rearrangement. This is known as Eschen-Mosher-Claisen rearrangement. Now coming to the next question. What is the product of this Wittig rearrangement? So in this week, we have seen Wittig rearrangement. So what is the product that we will be getting? This is the starting material. The starting material is treated with butyl lithium and then quenched with proton source. So what will be the mechanism and what will be the product that we will be getting? So here, in the presence of butyl lithium will be acting as a base. It will abstract the acidic proton. So the acidic proton will be present here because it will lead to formation of a benzylic anion. Benzylic anion will be more stable. So this proton will be abstracted and we will get this intermediate. Now it will undergo a like 3, 2, 1, 2, 1. 3, 2 or 2, 3 sigmatropic rearrangement. So this anion will go and attack over this double bond. It will shift over here and this bond will break, leading to formation of this intermediate. Now since it is an O minus alkoxide, so it will abstract the proton. We are treating with H3O plus. It will abstract this proton from H3O plus and it will get protonated, giving this product. So this is the Wittig rearrangement. It is completely different from the Wittig reaction where we will convert the ketone or carbonyl into an alkene. Okay. So here the acidic proton will be abstracted. We will get an anion and that anion will undergo rearrangement leading to formation of this alcohol. So the ether is getting converted into alcohol in case of Wittig rearrangement. Is the mechanism clear? Now coming to question number 8. So identify the retron in the following molecule, then draw the starting material. Go back only one step that will yield the target. So they are asking, this is the target molecule. So we have to identify the part of this molecule so that we will get the starting material. So here there is a 1, 2, 3, 4, 5. 1, 5 diene which could be obtained after the 1, 3, 3, 3 sigmatropic rearrangement. So here this is a 1, 5 diene. So we can do a backward 3, 3 sigmatropic rearrangement. So this bond can attack over here. This will shift here and this will shift here, leading to formation of this. So this will be the starting material. So as you can know, this is the retrosynthetic arrow. This is the retrosynthetic arrow. So this will be the product and this is the starting material. Okay. So this can also be redrawn in this fashion. If we redraw it, it can be written in this fashion. Okay. Is this clear? Now coming to question number 9. Propose a mechanism for the following reaction. So the mechanism involved 4 step, which involves 2 sigmatropic rearrangements. So this is the starting material. So it is getting converted into this product in the presence of this Wittig salt and under reflex condition. Okay, so this is involving a 4 step reactions mechanism, which is involving a which will involve 2 sigmatropic rearrangement. So we have to draw the mechanism for this reaction. So here this is the system. So we can label it like 3, 2, 1, 3, 2, 1. Now we can see like it can undergo a Claisen rearrangement. A Claisen rearrangement can take place 1, 2, 3, 4, 5. It is a 1, 5 diene. So it can undergo a Claisen rearrangement. Now after Claisen rearrangement, this bond will shift over here, this will shift here, this bond will break leading to formation of the carbonyl. So this is the product that we will get. So upon this carbonyl, the Wittig reagent, this asavitic reagent will attack and asavitic reaction will take place leading to this oxetane type of intermediate, similar to the Wittig reaction. Now this phosphine oxide will eliminate and we will get this product. Now this will undergo a retro-asa-Claisen rearrangement, that is a backward kind of reaction, a retro-asa-Claisen rearrangement. So we can number it like 3, 2, 1. Sorry, 3, 2, 1. So it will undergo a retro-asa-Claisen rearrangement and we will get this product. So it is involving 2 sigmatropic rearrangements. One is a Claisen rearrangement and the other one is a retro-asa-Claisen rearrangement. Okay, and in between, after this carbonyl is free, it will undergo a Wittig reaction and it is involving, it is shown in 2 steps. Okay, first leading to formation of this 4-membered intermediate and then elimination of phosphine oxide leading to formation of this precursor for retroacylation rearrangement. Clear? Now coming to question number 10. What product is generated in each of the following reaction? So this question number 10 belongs to 1,3 dipolar cycloaddition reaction. So here we are having a 1,3 dipole and this is the dipolar of 5. Similarly in case of B, this is the 1,3 dipole and this is the dipolar of 5. This is an intramolecular version of 1,3 dipolar cycloaddition reaction, and here this is intermolecular. So here this is the 1,3 dipole, this is the dipolar of 5, and here this is the 1,3 dipole and this is the dipolar of 5. Now we will see the mechanism, hence we will be able to predict the product. So we can see this is the 1,3 dipole. So this O minus, it will go and attack on this carbon of the dipolar of 5 and this double bond will go and attack on this carbon and leading to neutralization of this positive charge on the nitrogen leading to formation of this isoxazole. Okay, this negative charge will go and attack on this sender, this double bond will go and attack on this carbon leading to neutralization of this positive charge on the nitrogen and it will lead to the formation of a 5-membered cycle and that 5-membered cycle is known as isoxazole. This is the nomenclature for this ring. Now we are having the dipole and the dipolophile in the same system. So this is the dipole and this is the dipolophile. So the dipole will go and attack on this carbon, carbon number 8, and this double bond will go and attack on this carbon number 3, and this double bond will be broken, and this positive charge on the nitrogen will be neutralized. So this we can redraw in this fashion for our easy understanding. So this could be redrawn in this fashion, and this bond will be going attacking over here. This bond will attack here, and this double bond will be broken, and positive charge on this nitrogen is neutralized, and we will get this ring. This is 1, 2, 3. It is a three-membered kind of ring system. So these are some examples of 1,3 dipolar cycloaddition reaction. So the first example that we have seen is an example of a in intermolecular 1,3 dipolar cycloaddition, where we are having the 1,3 dipole and the dipolophile separately in the medium, and in the second case the same molecule is having the 1,3 dipole and the dipolophile within itself, and upon heating it will undergo an intramolecular 1,3 dipolophile 1,3 dipolar cycloaddition, leading to formation of this complex ring system. Now coming to the question number 11, which is dealing with the chelotropic reactions. So predict the products of the following chelotropic reaction. So chelotropic reactions basically involve the extrusion of stable molecules like SO2, N2, CO2, etc. So here we know that, as it is shown here, SO2 will be eliminated, and what will be the other product. So this is the starting material. It will undergo chelotropic reaction, that is extrusion of SO2 and some other product. So we have to predict the other product. So this is our starting material. So what will be the arrow pushing? So this double bond will shift over to here, this will shift over to here, and this will shift over to here. So we will be getting ET double bond Me. So we will be getting a diene like this. It can further undergo electrocyclization reactions under the same port, but here we have been asked this product. Okay, SO2 will eliminate, and this will be the product that we will be getting. Clear? Now coming to the next question. So we are having this as the starting material. So it is undergoing some reaction leading to formation of this and nitrogen molecule. So similar reaction we have seen in the previous question. So it is easy for us to address this question. So what is the name of this pericyclic reaction? Is it a cycloaddition reaction? Is it a sigmatropic reaction? Is it an electrocyclic reaction? Is it a chelotropic reaction? So it is involving the elimination or extrusion of small molecules, small stable molecules like nitrogen. Here it is nitrogen. So it is an example of a chelotropic reaction. So we can see the mechanism like this. This double bond will shift over to here. One second. So here, this negative charge on the nitrogen will shift over to here. Now this is neutralized. So this bond will break. It will shift here. This will shift over to here. Now, as we can see, Here a new bond is formed, COOET and methyl, and here there is only a single bond now, methyl, new, and this nitrogen is getting eliminated. So this is an example of chelotropic reaction. Clear? Is there any doubts or something? So today we have discussed some problems addressing sigmatropic rearrangement and some questions on chelotropic reactions. So in the next week we will be discussing problems on in reaction and organic photochemistry we will be starting. So if you are having any doubts, you can ask in the comment section of the video which I will be uploading in the YouTube channel. So we can meet on next Sunday, that is 3 March. Thank you.